Okay, thank you so much for the introduction, and thanks for having me today. So first, I'd like to thank everyone joining the webcast for attending today. I hope you're going to learn a lot about what we're doing at Nvidia to support the creation of self-driving vehicles. I'd also like to thank Nicolas Kumczewski and Yen Pham, who are both online and are going to help us triage through questions while the session unfolds. And at the end of the session, we'll go through Q&A. I hope to dedicate 10 to 15 minutes for it so that we can tackle some of the questions you guys have. All right, so let's see. So first of all, building AI for autonomous vehicles is an incredibly hard challenge. There's two main reasons for that. The first one is the incredible diversity of models, deep neural nets that have to be created to essentially support the creation of a self-driving car. The reason for that breadth of functionality is that you have to provide a rock-solid perception of everything that surrounds the ego vehicle. So from moving obstacles to things that are statically grounded around the vehicle, you have to build a solid understanding of everything around the car. And the second reason is the fact that you have to essentially make this functionality work across thousands of conditions and geolocations. So that's a big diversity problem. And in these conditions, think of this as the diversity of light conditions, time of the day, weather conditions, things that you can encounter on the road that are incredibly rare, things like road hazards, animals, rare, but when you actually encounter them, the danger and the safety problem is incredibly high. So put another way, you have this breadth of functionality that has to be built, and this incredibly large array of conditions that have to be met, where you have to develop and prove that the functionality works well. And so this essentially results in an exponential need for data and compute to support the development of an AV. Looking at the numbers, which is, I think, a great way to build a mental model for how complex the task is. We're essentially talking about driving a fairly large car fleet to essentially build up all the data we need to train these deep neural nets and validate them. The driving is typically 6 hours a day for a car times a few dozen cars. So you essentially end up in a place where you generate north of 1 petabyte of data on a daily basis. And out of that data, you essentially have to organize it, curate it, get it labeled, consume it into training pipelines to actually train and produce these deep neural networks. And then lastly, you have to actually validate the networks with two techniques that we call replay and simulation. And I'll spend a little bit more time explaining what those two things are. So in terms of scale, given how much data we can produce on a daily basis, you rapidly end up with this problem of curation, which is how do you actually select the frames that are going to best help you solve the problem, which is to train perception for to support the AV functionality. And then the second types of problems you have is how to scale labeling so that you can annotate all this data to support DNN development. So the scale is quite large. At Nvidia, we've developed a platform that's called Drive. So we think of it as a platform that enables the full creation of a software-defined car. So it includes both hardware and software. At the hardware level, we have a platform that we call Drive AGX. It comes in two flavors, Xavier and Pegasus. The goal with this hardware platform is to essentially provide enough compute capability that we can support a pretty rich and diverse software to run on the platform. The software itself is going to go from anything around the AV functionality itself, so supports the execution of perception, which is extremely intensive in terms of compute because we have several sensors around the car, and deep neural nets are typically quite intensive in terms of compute. To applications at the upper level of the stack, like our Drive IX stack, where the idea is that we're providing functionality to essentially monitor the driver in the car. So for things like attention, is the driver being distracted, and so on. So all of this adds up to a lot of functionality that requires both compute performance and flexibility in terms of software, so that these things can be rapidly redefined and changed over time. Drive is more than an embedded platform. It's also a full development platform that lets us actually support the development of AV. So to build an AV, I mentioned a few of the challenges in terms of scale of data. There's also other types of challenges that we have to tackle. The very first one is what we call continuous engineering. For data collection, training, simulation, validation, testing, and deployment, AV is not a static problem. It's not a thing where you essentially build the software once, validate it, and ship it. You can think of it almost as a living organism where quality has to be continuously improved, data has to be continuously collected from the road, bugs have to be fixed in a continuous fashion. And for that, you need an entire tool flow that supports this continuous improvement capability. Associated to that, there's a big need for a strong infrastructure, tools, and methodology. So infrastructure, pretty trivial to understand why, because we have to deal with data sets that are so large and organizing them and supporting the training and validation of these deep neural nets. That complexity alone requires a lot of infrastructure. Tools and methodology, two primary reasons why that's so important. One of them is organizing the development of these data sets and training of these neural nets, reaching very specific safety KPIs, targets, metrics is something that's not trivial and requires the infrastructure to really support a methodology that's clearly articulated. And another reason is that you really have to be able to essentially trace everything that happens on the road. So any bug you may encounter back to what actually caused that bug. Was it a lack of proper data to support the problem? Was it an issue at the architecture level of the deep neural net? And so your infrastructure and methodology needs to support this end-to-end. Third tenet, algorithms and software. AV is a place where we're still innovating at an incredibly aggressive pace. On a monthly basis, we introduce new methods, new techniques to better train these neural nets, save on what data we have to label. So you need to have a framework and platform that supports this innovation and supports the idea that you can continuously change these algorithms. And so this means multiple things. One of them is the in-car platform, the embedded platform, has to support a rich array of software capabilities. The more general purpose you are, the more you're going to be able to adapt to new ideas and new techniques being defined. And then second, the end-to-end infrastructure, including the car side and the cloud side, need to be really well thought through together to enable that type of rapid innovation. And the last big part that's really important is unified fleet management. So you really need to think about your fleet of cars as a key element of this whole pipeline, because it's both where you deploy your software, but also where you collect your data and get your bugs from. And so it has to be tightly integrated into the rest of the platform. And so for that, Nvidia has been developing this platform we call Drive, and we think of Drive as really enabling this end-to-end product lifecycle. So let's look at the lifecycle itself and the process to develop an AV. This is how we think of this end-to-end process. So it all starts with the car fleet on the bottom left side. The car fleet is, as I said before, both where we deploy our software and where we collect our data from. So each car is essentially instrumented with a set of sensors that are running in our production environment. So we have cameras, we have LiDAR, we have radars, IMUs, all sorts of sensors that essentially help us understand the environment and surroundings of the car as much as we can. From that, we essentially ingest the data into our data center. And the first big important box is what we call generating data sets. So this step is critical because that's what feeds the entire pipeline downstream. So generating data sets is really about organizing all the data we collect into data sets that are either going to be used for the training of the models or their validation. Downstream of that, we have this box that we call generating models. So this is largely gated by the training of the DLNs. So this requires a lot of GPUs to essentially support the training of these models. In that box, we do a lot of things like hyper optimization, AutoML, finding the best models to fit these data sets we have. Then the next step is to develop the AV software itself. So the AV software essentially consumes these models that we've trained. And then there's a lot of extra logic around it. So pre-processing, post-processing, control and planning, mapping technology. All these other algorithms essentially constitute the entire AV stack. And this is entirely based on our Drive AV software platform. And then downstream of that, the very last step, and one of the most important of the pipelines, is the validation step, where we essentially take a final AV build and make sure that it passes a long list of tests that essentially capture what we expect the AV software to do. So for us, validation is made of two big components, replay and sim. Replay is essentially based on collecting real sensor data from the road and essentially replaying them through our AV stack offline in the data center and validating that all the predictions from different signals in our stack do the right things. So this typically requires the data to be labeled partially, sometimes less for things that require mostly an analysis of the signals being produced without a check against ground truth. And then the second big box that we call SIM is essentially a full-blown simulator that simulates the sensors themselves and enables to do full closed-loop simulation of our AV stack. So this is very interesting because it lets us essentially test the full system just as if it was running on the real road. And the only downside is that the sensor data itself is simulated and therefore not a pixel accurate. And so we'll spend a bit more time on SIM because it's such an important aspect of our platform. Okay, so these six big components, Drive AV, our fleet management, Drive Data, Drive Train, Drive Replay, and Drive Sim, are essentially all enabled by this unified development platform we've built at Nvidia that is essentially made of two big components. On the left side, you're looking at our embedded stack. Drive AV, DriveWorks, DriveOS is our software stack, all sitting on top of AGX, which is our embedded hardware platform. And then Hyperion is the code name for our sensor platform. And so on the left side, you have essentially everything that's running in the car. On the right side, you have our data center stack, which is running entirely in a data center or on the cloud. And it's running on two base hardware platforms, DGX and Constellation. DGX is essentially general purpose GPUs that are used to provide most of the compute power for the training and replay of models. Whereas Constellation is essentially our embedded SoC AGX, which is essentially running in a racked up version in the cloud so that we can actually do hardware in the loop simulation of our stack. So I'll come back to that later. This is a really important aspect of this platform. Constellation essentially enables us to validate our AV software just like if it was running on the real car, except it's in the cloud. And then on top of that, you have this software layer we call Apollo, which is essentially an infrastructure as a service which abstracts away all the addressing to the hardware, the scheduling, orchestration, storage. And then on top, you have this platform that we've developed internally at NVIDIA called Maglev. And this is really the layer that provides all the functionality to support our end-to-end development, from dataset management to the workflows, essentially feeding these datasets into the different parts of the AV development pipeline, whether it's training models or supporting other things like mapping creation, and then ultimately the validation at the very end of this pipeline, so replay and sim. All right, so what I'd like to do next is spend a little bit of time on the types of high-level problems we have to solve to really enable the creation of an AV. So we're going to start with what we call data-driven AI development, which is largely focused on this first box in our pipeline. So how do we actually create the best and the correct data sets to support AV development? So that, in some sense, is a problem that's faced by anyone who is developing AI these days. When you deal with deep neural nets and you have to create models for something, your quality is heavily gated on the quality of your data. And you need your data to accurately represent the problem you're trying to solve. So in some sense, with AI, we've shifted the problem of designing algorithms to designing data sets that accurately capture the problem we're trying to solve. So there's two techniques that we're going to go over now. The first one called active learning, which you can see in the bottom arrow. So the idea there is that we want to be able to leverage the models we've trained to essentially select and help us build our data sets in a way that's as automated as possible. And then second, we'll go over what we call targeted learning, where the idea is that, in this case, the upper arrow, we go all the way to validation, deploy our stack, and test how it does in large-scale scenarios, and then look at all the bugs and start from these bugs to essentially help us correct and improve our data sets. So first, taking a step back, I'd like to look at the typical deep neural network iteration cycle. So anyone who's been interacting with deep neural nets or machine learning in general, for that matter, has gone through this typical cycle. The cycle typically starts in a way that's extremely manual and labor-intensive. So there's a first step that's about selecting the data. Any new project starts with doing this largely manually. So out of a large body of data, we're going to pick some data in a way that's almost random. The second step is about labeling the data, so annotating the data to actually teach the algorithm to predict what matters. Then third, adding that data to our training data sets. And then fourth, actually training the models on that data, getting insights from it, understanding how the model does, and then repeat that cycle. So that cycle it turns out that it's actually quite human intensive, requires a lot of labor to actually organize the data, manually select it, label it, and it's suboptimal in many aspects in the sense that the selection process has a huge impact on the quality of the models. And if you don't do this in a more principled way, you'll be limited in how far you can really push these models. So where active learning comes in is this fundamental idea that we'd love to essentially use models as a way to query raw data and help us select raw data in a way that's more principled. So the idea now is that we start from a step that's called crawling data. So that step basically starts with the pre-trained models. And it's going to use that pre-trained model to query the data and compute some notion of confidence for each data point and help us select the data that's the most confusing for the current model. So if you have a good way to estimating confidence or confusion, you'll have a great mechanism to essentially select that data and make sure that as you build up your data set, the data you select and label is maximally impactful for your task. So this is significantly better than doing things manually, but it also requires a lot of infrastructure to get this right. And the reason for that is that you need infrastructure to essentially apply models on large bodies of unlabeled data. On a typical AV data lake today, you'll find anywhere between 5 to 10 billion frames that are unlabeled and that you can use as candidates. So this is incredibly expensive to actually score. But once you've done that, you end up with a large array of candidates that you can use and prioritize for labeling. So our end goal really is to automate this entire cycle such that the way we create the data sets are as informed as possible from our current performance, from our current models. So in a nutshell, active learning is really about optimizing data selection by having the models tell us what they need. And second, the idea that automating the model delivery loop by providing the right infrastructure to reduce human intervention as much as possible. Ideally, what we'd love to be is to have humans only enter this picture to help annotate the things that we really cannot figure out on our own. So the things that you actually want to teach the algorithm. But everything else, including the selection process and what should really go into building these training data sets, should be as automated as possible. These days, we typically implement active learning with pool-based methods. So there's quite a bit of literature on that. Our team has actually produced a few interesting papers on the subject as well. And the idea is that we're essentially selecting data from large arrays of unlabeled data based on a confidence score. The confidence itself can be computed many ways. And the best way to do this is to do it empirically through A/B tests. So I'll give you a few examples of, first of all, why active learning is so sensible, and then next, the type of A/B tests we've been doing to validate that. So why is active learning sensible? I really love showing this picture. intuitively, if you kept your sampling data randomly from large arrays of data collection campaigns from our car data, you would end up with a lot of data like on the left side. But really what you're interested in is finding all these corner cases like on the right side, where you really need to have a lot of focus of your algorithms to understand and model these situations properly. And so the only way to find something like the right side image is to actively bias the sampling and use your models to tell you that they don't understand the scene. So one A/B test that we've done at scale, which was really telling and led to really interesting results for us, was to essentially use our DriveNet model. So DriveNet, for a bit of context, is one of the models that we have in our Drive stack, which essentially focuses on pedestrian and vehicle and bicycle detections. So essentially two main things. It's detecting all the main dynamic objects around the ego car. And the focus of that study here was on vulnerable road users, what we call VRUs in the industry. And so these are basically pedestrians or bicycles. So any moving target on the road that's a high-risk object that you really don't want to hit. And so the problem we tried to solve here is how to improve the performance of VRU detection in difficult conditions like nighttime, for instance. So what we did in the A/B test is we essentially pitted two methods against each other. One of them was to continue manually selecting data. So we asked our curation team to essentially go find a lot of examples of pedestrian data at nighttime. So they used our data lake, they used our platform to go query these images. And on the other, we essentially tasked our model to directly go find these same examples automatically. So that's an example of what the model came up with. So when you go through these images, what's interesting is that the model is going to mine both examples of pedestrians or bicycles that are confused under the current model, but it's also going to find examples of background scenes with no pedestrians where the confusion is also there. So unlike a human, the algorithm can also tell you the negative examples it's confused about. So doing this and running an A/B test at scale, which was quite involved because this means that you have to essentially go label data from both the manual selected pool and the actively selected pool. We ended up showing that active learning led to considerably better results. So particularly for things like bicycles here at nighttime, where we showed a 5x improvement compared to the manual baseline. So the short conclusion here is that active learning is an extremely effective method, and it's a great way to organize this process of building data sets to solve large-scale AI problems. But obviously, it requires quite a bit of infrastructure to put everything together. So from the inference at scale to actually score the unlabeled data, to piping these things into a labeling pool, to then retrieving the results, doing proper A/B tests, consuming these labeled data into training sessions, and then validating them. These steps are quite hard to stitch together, and this requires good infrastructures and tooling to support. And so I'll come back to that side of the problem in a further section. Another instance of this family of methods is what we call targeted learning. So I'm coming back to the same diagram. With active learning, we have a method that essentially lets us automatically find the worst problems in a data set based on the current model we have. The second method that we call targeted learning actually starts from a bug. So starting from a bug is a different capability that's really important to have. So imagine that you've deployed an heavy software stack to the road. It's been used by several thousands of cars in different countries in the world. And then suddenly one day you have a bug, you have a new type of object or car or vehicle on the road that's poorly detected. What you'd like to do is being able to log that bug, collect examples for it, and very rapidly go through fixing it, essentially. So in this case, we're going through the same cycle, but we're now starting from a reference piece of data that we'd like to address as fast as possible. So conceptually, the way this works is it's typically entirely based on querying similar images from the reference one, and then having the ability to add these to a training data set rapidly. So here we've done several experiments around querying images across our entire data lake. So what we're looking at here on the top left corner is an example of the bug that would be logged into the system. And then the rest of the session is every hit that's coming back from our database. So you can see that these are different types of trucks. They all have the same orientation. They're all in similar conditions at night. So this type of technique is incredibly useful in the sense that once you have this bug, you can go query a significant amount of similar data, add this to your training set, retrain your model, and then redeploy it. So this is something that's analogous to active learning, requires extremely similar infrastructure, but instead of being a closed loop system, it essentially starts from a reference bug. Okay, so these were two techniques to essentially support the development of AV based on real data. At Nvidia, we've been interested in essentially complementing that and expanding our abilities with simulation. And so we started this project a while ago, which is called Nvidia DriveSim. So lots of public information on the web about DriveSim on YouTube, on Nvidia's website. I invite you to look at it. In a nutshell, DriveSim is essentially a full-blown AV simulator that renders graphics, has a full model for sensors. And the way we typically deploy DriveSim is on a computer that we call Constellation. So I'm going to start at the bottom of this picture. Constellation has two sides. The left side, which is the simulator itself. So this is basically a general purpose graphics computer that's hosting the simulator itself. And on the right side, you have the other side of the Drive Constellation computer, which actually embeds our AGX embedded computer that's running in the car normally. So this is literally the computer that's deployed in the car. We've put it into a rack, and we've connected all its inputs. So all the inputs that normally receive, camera sensors, LiDAR, radars, and we've essentially connected them to the second box on the left side. And this whole rig essentially enables you to do something that's really cool. You can run a full simulator on the left side. You can run our full AV stack on the right side. The sensors being rendered by the simulator are streamed through the right side into the AV stack, and the AV stack thinks it's basically driving. It's issuing control signals back to the simulator, and it's essentially driving in that virtual world. So this lets us do all sorts of things, and in particular, it lets us really expand how much testing we can do to support our AV development. The way we use SIM today is primarily as part of our continuous integration and regression stack. So for traditional software development, CI tests, continuous integration tests are typically tests that we write to validate the behavior of software. And these are run each time our code changes and gets pushed into our code repository. For AV, the continuous integration and the idea of regression tests is essentially entirely different because it's going to be based on real data and real scenarios that you want to validate your stack against. And so what we had to do to support this is to essentially rack up these whole Constellation system plus the SIM stack plus the AV stack and make it available at scale as part of our CI system so that we can enable daily testing and regressions. So a few examples of what SIM can do for us. So this shows you a few examples of environments that can be generated with SIM. So Nvidia is obviously well known for its abilities to generate world-class graphics. Recently, we've invested in really cool technology that's called RTX that gives us real-time ray tracing as part of our latest generations of graphics cards. All these goodies essentially end up propagating into our DriveSim stack. And this lets us build models of the world that are incredibly realistic in terms of visual details. We also have great sensor models, models for weather conditions, time of day, and so on. And so the output is quite amazing. And through various APIs, you can essentially script multiple environment models and generate scenarios that are quite rich. So I particularly like to look at the great models we have for weather conditions, so fog, rain. And the reason this comes in really handy is that it's typically really hard to actually collect such data on the road. So particularly where we live in California, rain is not that frequent. In simulation, you can basically live all year long in the rain if you so desire. So one thing that makes DriveSim being used quite effectively by our team is it's entirely scriptable. So we have a scenario description language with a Python frontend, so that lets the team essentially rapidly create scenarios, script the initial conditions for the ego car, and then all the surrounding cars around the ego car. And then from then on, the AV stack can take over and start driving in this virtual world. So what's so great about this is that you can offload a lot of the daily testing and bug finding from on-road testing to fully virtual, and let the team go explore thousands of parallel scenarios on a cluster instead of going to the road and being gated by a few number of cars. So through scripting, you can essentially really sweep through all these matrices of conditions that I mentioned at the beginning of the presentation, and go render scenes that cover a very large array of weather conditions, daylight conditions, day versus night, and so on. Okay, so I want to show you two great examples of how we're currently leveraging our simulation stack for data augmentation first. So at the beginning, I also mentioned that some types of conditions are extremely hard to actually find on the road. So one great example is hazards. So things like, sometimes you drive on the highway and you're going to find a mattress or a card box or any object that fell from a truck. These are incredibly dangerous hazards on the road, and yet they're incredibly hard to find. So if you go drive around with a data collection car, you will find such things once every 100,000, 10,000 of hours of driving. So these are really rare events. So what we wanted to do here is start leveraging SIM in a kind of hybrid setup where we would essentially render such hazards, and then with a masking technique, essentially imprint them on real scenes. So here we can do all sorts of things, like either training our models on straight simulated data, or training them on a hybrid of simulated and real data. And so we've started training models on these types of examples where the hazards are imprinted on top of the real data. And then what we've done is we've started validating that on real hazards that we've put in all sorts of scenes outdoors next to our office, and essentially shown a really amazing transfer. So in this case, the models are perfectly capable of detecting real hazards on the road, whereas the bulk of the training was done on synthetic ones. Really exciting stuff. The other great utilization for simulation is for validation. So validation, obviously, of the full stack is something that SIM is naturally well suited for, because we can do closed loop control. But there's also all sorts of other things that are typically manually intensive, labor intensive in the real world, that become really trivial in simulation. So this example here, most of our current perception stack at Nvidia is trained on a reference car where the sensors are roughly, so the front camera, for instance, is roughly at 1.4 meters from the ground. And what we want to do is have the ability to adapt our perception stack to work on all sorts of other vehicles. So on the left side, we're showing the front camera being moved down to the equivalent of a roadster, which would be pretty close to the ground. And on the right side, you have the front camera moved all the way at the top of a semi-truck, so 2.8 meters from the ground. That's close to 9-10 feet. And so you can see the different viewpoints. And so this typically affects your perception performance. Through doing these types of real tests in the real world is quite labor intensive, because you essentially have to create a rig where you would move the camera up and down at the front of the truck, for instance, and then go collect some data, label the data, compare the results. What we can do with SIM is essentially fully abstract this away, virtually move the sensors in the ego car, and then plot out these types of metric curves. And so here what we're showing is a specific deep neural network we have that predicts the distance from the next car ahead of the ego vehicle. And it's showing the impacts that changing the mount on the ego car has on the KPI. And so what this shows here is that the relative error is actually quite low, meaning that our perception on this front camera is actually quite robust to the vertical position, which is what you want. Okay, so we've looked at two big problems to solve. The first one was about organizing our data sets and having great techniques to essentially organize them in a way that's scalable, so active learning and targeted learning. And then we looked at the role of simulation to help us expand our abilities to essentially create data for corner cases. Next, I'd love to go over some of the key ingredients that are required to build an effective AV development platform, and so essentially support what we just looked at. So I'm coming back to this first diagram. So we looked a little bit at what DriveSim can do for us. We also looked at our Drive data box and types of things we can do to help us better organize our data sets. Today, in the interest of time, I'm just going to spend some time on a handful of these components. I'm going to start with the workflow box in maglev. So workflows is an essential part of such a platform. There's multiple reasons for that. The first one, I think, is really the fact that if you look at this AV development process, you have to go through a lot of steps to essentially build and validate an AV. First, you have to essentially pre-process your data and organize these data sets, do inference on them, compute all sorts of attributes like ego motion, calibration on these data sets. Second, you have to train and explore a large array of deep neural nets, do things like AutoML, hyper-optimization to essentially find the best possible models for the task. Third, you typically have to optimize these models for inference so that they fit in a finite compute budget, even though we have a tremendous amount of compute power on our embedded stack. Embedded hardware, we still need to optimize for that footprint and pack as much as we can. And then fourth, once you have the models, you have to essentially run through these fairly complex validation workflows. So whether it's replay on real data or via simulation, which we just showed, these workflows are quite advanced and they need to be organized. And so what we decided to build a few years back is essentially a unified workflow management stack that would support all these different types of workloads. Let us run these jobs on a heterogeneous cluster, so general purpose GPUs on one side, constellations on the other. And the end goal was really to have one single workflow platform to essentially organize all these jobs, do things like large-scale data processing jobs that are distributed as MapReduce jobs, do things like AutoML, where you want to distribute many training jobs in parallel on many machines, do things like multi-node training, where one single job is going to train on multiple nodes, do things like distributed replay inference, inference to mine data for active learning. So essentially support all the use cases I showed before in the presentation. So this workflow platform we've built is for now internally available at Nvidia only, and something that's used across our whole AV team. On the one side, it supports the definition of our training pipelines really well. So this is a picture showing a typical workflow for a training job that's essentially alternating between training and validation steps. And then it's also fully integrated into our ingestion and data ETL pipelines. So once we get data from our car fleets, whether it's coming from our test cars or our data collection fleets, data gets ingested into our cluster and it gets pushed through this fairly complicated indexing and data pipeline that essentially organizes the data, indexes it, and makes it searchable for further curation or exposes it for jobs like active learning. And so then the output of that is data that's going to be consumed by things like tagging, labeling as well. So again, having a unified workflow platform is probably one of the most fundamental things that we had to get done. Second part, obviously, is compute. And so here at NVIDIA, we've deployed and built and grown a data center that's completely specialized on GPU compute that we call Saturn V. Lots of public information about Saturn-5 as well. So as a whole, Saturn-5 provides 2,000 DGX nodes. Each DGX provides 8 GPUs, so that's 16,000 GPUs total. So in terms of compute power, it's an aggregate of 1.8 exaflops, and this is serving roughly 1,000 unique users across Nvidia. So AV, specifically the development of autonomous vehicles, uses a subset of those DGXs. But the key thing for us was the ability to address these DGXs through that unified workflow system that I just mentioned. The second big part that's really important, and I brushed over this when I talked about simulation, is this box that we call Constellation. So Constellation is quite interesting. You can think of it as essentially a full hardware-in-the-loop system simulator solution. And so it really comes with two boxes. One box that's providing the general purpose GPU compute to actually render the simulator. This box needs to be quite powerful in terms of graphics capability, because you need to be able to render as many sensors as you would have on a real car. A high-end car can have anywhere between 8 to 12 to 15 cameras. And so you need to be able to stream render all these streams and actually stream them to the other nodes. And the second node essentially bundles up AGX, which is our embedded platform, into the rack and connects it to the other one. Again, same thing, Constellation is fully racked up in our data center. And we're addressing to a similar workflow stack. And the key thing for us is that we're able to essentially treat that Constellation cluster as essentially a virtual fleet of vehicles on which we can deploy arbitrary changes to our software stack and regress it against any of the scenarios we have, whether on real data or through our simulation stack. Okay, and last, I'd love to give a sense of how all these things have come together for us in terms of infrastructure at Nvidia. Our end goal when we built this infrastructure was to really get to a point where we would be able to have a lot of automation and traceability. So these two concepts are fundamental to developing AV, and I believe that in the future they will be fundamental for other applications like robotics, where safety is also a concern, and healthcare applications. So first, automation. The idea of automation is that you want to get to a point where you can really decouple the machine learning, AI, algorithmic development from the production of these algorithms and what's being shipped into the car. So what we're looking at on the picture is at the bottom, you're looking at a typical machine learning developer who is doing three things. He's developing the applications themselves, so coming up with new neural net architectures, new post-processing techniques, new CV algorithms, new pre-processing pipelines. Second is typically running these applications in a way that's fairly interactive on a daily basis, so manually running these applications on the cluster. And what that person needs is to essentially have a lot of rapid feedback on whether his algorithm makes sense and is better than some baseline. And then last, that person wants to be able to get results and really understands what worked and what didn't work, and then iterate and learn from that and continue that process. At the top, you have what we call a production engineer, whose role is slightly different. The production engineer is essentially going to be focused on really turning the crank, optimizing the performance of applications, making them faster, both on the training side and on the inference side for the deployment. He's also going to be responsible for the deployment of the final applications and the publication. And that production engineer can essentially run the same workflows in a way that's a little bit more graduated in terms of quality, and potentially fully automate things like active learning, so that given a fixed algorithm and fixed processing pipeline, that person would be able to go improve the quality of our data sets continually over and over and over. And so what we're trying to show here is that the system we built really needed to accommodate and optimize for these two personas. On the one side, the ML developer who needs to iterate and innovate at a rapid pace. On the other side, the production engineer who needs to take these final algorithms and turn the crank, improve data sets, and ultimately publish the models. So that platform we've developed, Maglev, the unified workflow stack, these are all components that really support this vision. Second topic on that slide, traceability. So again, one thing that we did from the very early days of this project was to make sure that through this unified workflow system, a strong management system for data sets, every experiment we would do and every model we would deploy to the car would be fully traceable back to the original data sets, the original code, the original models used to actually support the release. The traceability is critical, obviously for safety reasons, but also for development health. The more you have traceable results, the more you can reproduce and understand what model linked back to which data, the better you can organize your workflow and debug things effectively. All right, and on that note, I think we're ready for a Q&A. So thank you very much for listening this presentation.
Great, thank you. So just wanted to take an opportunity to remind everyone that you can ask a question using the Q&A window to the right of the slide presentation. And so we'll just give our speakers a moment to look over the questions. And we have some guests as well. So please begin when you're ready.
I'm Nico Kumczewski, so I'm here to start answering the questions. So I put a few down, you know, like to answer at the end. I tried to answer a few during the talk. There are still a few ones coming, so someone has to basically triage them. Okay, so one of them was, let me see, and I think I replied to all, but I want to make sure that this is clear for everyone. So, how do we upload petabytes of captured data from driving tests? So I think that's a good question, right? Because this is a challenge actually. So what we have is, you know, like a certain number of cars driving, and when those cars are really dedicated to data collection, then we can end up with really large amount of data per car, you know, in the order of a few terabytes. And so in that case, we need to be able to load those 4 terabytes, I mean, like few terabytes to the cloud. Since we don't want to interrupt drives by, you know, maybe waiting for the data to upload over the Wi-Fi, for example, we have a dual system, one over the Wi-Fi and one over the one over like a physical machine. So the way it works is that we have a few machines that are dedicated for data upload across the world, where drivers can, you know, usually in like garages or like next to where we're supposed to drive the car, and then we can plug the SSD, copy the data locally, which is really fast, and then the driver can go back to do their work, and then regularly the data is going to be uploaded to the cloud. And then it takes quite a while to upload, right? Because these are terabytes of data. So we can, you know, maybe a few hours or something. But then after that, we have a really like beefy workflow basically to process that data, test it, index it, organize it, process it, you know, everything we need in order to make it available to everyone. So that was like, yeah, I think that was an important question. So I wanted to make sure everybody would know.
Great, yeah, thanks, Nico. I think I can try to take a second one. So there was a question about whether our infrastructure provided a full data labeling workflow management system as part of maglev. So the answer is yes. We do have a full tool chain that essentially provides everything we need to organize our data pipelines into labeling workflows. Labeling for us has become something that's quite complex and advanced. Now we think of labeling as really producing ground truth for our various efforts. So one type of ground truth effort that we have, for instance, is the production of 3D ground truth, where we essentially leverage our LiDAR data to help automatically label some of our camera data. In these types of workflows, you actually have both two components. You have one that's extremely manually intensive, where someone actually has to draw the bounding boxes. But you also have things that are automated, like the computation of distances and attributes in 3D space. And so these are hybrid pipelines where part of it is computational, part of it is manual. And we also do employ a workforce for labeling in India that's quite large, north of 1,000 labelers. And they basically work full-time on this platform to essentially produce all the data we need.
So I think I had another interesting question here. Yeah, how do we identify perception bugs? Does someone look at the videos manually? So I think that's an interesting question because Clément talked about the perception bugs and the fact that we had a system now that could automatically let us sample data in order to solve for perception bugs. And so the way those bugs are fielded basically is, I mean, there are multiple ways, right? Either they can be discovered when the car is running. So for example, the driver can see a situation and has like real-time feedback from the predictions via a UI and can say, okay, now I need to, there is a situation that's a little bit sketchy, or like I'm not detecting this and this and that, and then can actually activate press a button basically to schedule an event. That's one way to like trigger a bug. When the driver comes back from a session, they can say, hey, basically there was a problem at this time, right? So they would look at the video again. I mean, like quality assessment would look at the video and they would say, okay, yeah, there was an issue with perception, and then create a bug. And a final way to do it is more automatically, meaning running those videos through the system in the cloud and detecting when perception is making mistakes, right? And trying to cluster those mistakes together to basically collect like clusters of bugs, right? So an example would be, oh, my perception is not as good at night as it is during the day, and so this would also lead to a perception bug.
Okay, next question I'll take is, so there's a comment and question on what we showed about hazard detection with simulation. So the road hazard detection is amazing. You only showed images of recently paved roads. Can you simulate repaired asphalt roads, and does that make hazard detection more difficult? So I think we're really at the beginning of exploring this thoroughly. But the great news is that on the simulation side, we really have the ability to generate and simulate arbitrarily complex scenes. So we can really generate, potholes and complex elements in the scenery itself. So we're pretty confident that we'll be able to model those types of things. And then the question for us, of course, is how much are we going to be able to leverage from simulated data versus real data? So our core belief right now is that you need a hybrid approach. You still need a lot of real data to make sure that everything you do is grounded in reality, because that's ultimately our end deployment platform. But we do see that there's many cases where augmenting our real data with simulated data is quite effective. We've started doing it with hazards because that's obviously the thing that's the most difficult to actually collect. But we think that there's going to be many other places that we're going to be able to expand that to.
Yep. Okay, I have one question here. What are you using to schedule workflows on the large fleet of GPU machines you have in DGX Saturn? I think you briefly touched on this, Clément. But basically, yeah. So we have a lot of GPUs, GPU nodes, right? And we have a lot of CPU nodes too. And we need to perform a lot of various tasks on them that range from ETL, like data pipelines, to training pipelines, so on and so forth. And so this is quite complex, and also the number of like programming languages and stacks that we are supposed to run inside of this workflow system is really large. And so as a result, we developed our own workflow system. We developed our own workflow system to handle that scale and all these various use cases. And so what we are using, we're running this on top of Kubernetes. So we're using Kubernetes as the base scheduler, basically, and resource management system. And we are using the workflow system. We implemented our own workflow system on top of it.
Great. Let's see. So the next one I'll take here is a question on how many driving hours of data collection is needed and how much time you need from collected data to a trained model. So that's a great question, very open-ended. We typically collect anywhere from 10 to 20,000 hours of data on a yearly basis to essentially feed our base development needs. And this data essentially goes into two things primarily. So all our feature development. The deep neural nets we trained come in two kinds. Some are trained on static frames or short sequences of frames. And in these cases, we typically need anywhere from 300,000 frames or snippets to north of 1 million, 2 million such frames. So that's for one particular network. And so in aggregate, like you end up with an overall data set that's anywhere from 10 to 50 million frames across the different functionality we support. The time from collected data to a trained model is a bit of a tricky question. So our typical latency, so first of all, the way we collect data is still largely based on essentially sending SSDs via FedEx worldwide. And the reason for that is that FedEx is literally the system that has the highest bandwidth to transfer data. It has terrible latency, but amazing bandwidth. And so we have latency there from the moment we collect to the moment we ingest. But then the second piece of latency is how fast we can actually label the data. So that typically takes anywhere from 2 to 4 weeks to get sufficiently enough data to get labeled on a new ingestion piece. So this is how we do things in our offline development workflow. Then there's a separate workflow that's optimized for bug fixing, where the data is actually collected through OTA, so it doesn't go through SSDs. In this case, we have the data recorded in the car, we push it through Wi-Fi, and so this works for much smaller targeted data campaigns. And in this case, the turnaround time can be much more optimized.
Yep. Let me see. Oh, yeah, there was an interesting question here. And by the way, it's probably for you, Clément. Because this work seems only focused on camera-based autonomous driving. What about sensor fusion with LiDAR and radar or radar?
Yeah, okay, I can take that too. Yeah, so actually our platform is we have LiDAR, radar, IMUs, and cameras as first-class citizens. We're building a platform that can tackle both L2 plus type applications. So similar to what Tesla is doing on the road today, where the idea is that you have a camera only deployment and you have to do everything from cameras alone, potentially with some radars to help in some situations, to the other extreme where you have multiple LiDARs on the platform. So we have a partnership with Volvo Trucks today where we're essentially building a full-blown level 4 truck platform, and this depends on LiDAR. And so in this case, we essentially have multiple independent perception paths, one that's based on LiDAR alone, one that's based on cameras, and then we have fusion, and that's how we essentially bring our failure rates down for L4.
I have a question here about active learning. So for the active learning component, is there any heuristic-based approach that you guys use to prune the data search space or apply the approach to all possible images? Yeah, so thanks, because I think this is a very interesting question. So I guess what this means is, like, when we compute the uncertainty on frames, do we compute on the entire data lake or like data set of frames, or do we pre-select like a subset of frames? In the experiment we ran, we actually used a subset of frames that was already targeted for night data, for example, and trying to then look at uncertainty only for pedestrians. In general, the technique is applicable to both. I would say there are two modes. One is like trying to fix a bug, where when we try to fix a bug, then we're going to try to reduce the search space, but still use the active learning uncertainty as a ranker, basically, of the frames to select. And then when there's the continuous improvement track, which is the second track, where we want to improve the model continuously and let the model discover really like the patterns that it's missing, right? And so in that case, we want to look at the entire that data set. And so these two can live together, basically, and improve the model based on, like, short-term or medium-term bugs that are important, plus the long-term improvement of the model.
Yeah. One more question I can take here. Have you ever thought of the simulation as a video game where people could drive a car around and you insert AV to react to the human behavior? Yes, in fact, that's how we started. So in a lot of the early demos, we showed with DriveSim, we essentially had a human driver essentially drive a car and then next to it, the AV trying to basically drive around or not be disturbed by the car. But generally, the way we're thinking about this in the long run is that we want to essentially have AIs for all the traffic around the ego car, so that we can sweep a very large array of such behaviors. So instead of having just one human driver compete against the AV, we'd love to simulate and sweep through thousands, millions of scenarios to really go find corner cases.
Great. Well, thank you guys. That's all the time we have. I appreciate your being here and presenting and answering the questions.